you. Thank you to everybody to come here today, and thank you to give me this wonderful, but at the same time scary opportunity. So, as Chris already said, I'm Silvia Oggero. I'm ESR 1, and I'm working at Queen Mary University in the Biochemical Pharmacology department, which I like also to call Biopharmaly. My supervisor is Mauro Peretti. So, but let's go back to 25 years ago when I was born. I was born in 1991 in a pretty city next to the Alp called Torino, Turin. And basically, my entire family was doing their career in science and in medicine. And as, for example, my parents themselves, they are both pharmacists. Generally, what happens to kids is that they listen to their parents and they then take the same careers. So guessing what, in 2016 I graduated? Pharmacy too. But the year before this, because actually I wasn't sure that I wanted to be a pharmacist in my life, because I was already quite interested in science, I just decided to apply for an Erasmus scholarship, and I went to go 9 months in London to do my research program, my thesis. And this is when my journey with science started. There, I had the wonderful opportunity to meet people that helped me to understand how good is science, but at the same time, how frustrating it can become. But in any case, I liked it, so here I am. I'm doing this project in London. London, well, the amazing London, I have to say. London is great, lots of cultures, lots of people. You mix up with them and you don't get lost, because this is the way it works. So let's now pretend to be on the top of the highest building of London, the Shard, this one, in a rainy day. Sorry, I didn't find a picture of a rainy day of the Shard. They don't want it to exist, even if we are in London. So let's now pretend to look back to the street. And from that height, the only thing that you can see are actually spots, like black dots, red dots, blue dots. But again, what are they? So let's go now back to that street and let's look carefully there. Actually, there are buses, like the red dots can be double-deck buses or taxi cab, the black dots. And the blue spot can be a lady walking in the rain, trying to reach the way to work. But let's try to make this more scientific. Let's think about these buildings like cells, and the streets are like vessels of a body called London. What can we say about these things? What can we say about buses, people, cabs? What are they? What are they that we can only see when we zoom with something like a microscope? Well, I like to call them microparticles. What are microparticles? Well, microparticles, but nowadays people like to call them microvesicles, are little spheric objects that are released from every cell surface. They are part of a bigger family called extracellular vesicles, which comprehend other entities like exosomes, which are smaller, and we can compare them to people, to a bus stop, like they go outside from the bus. Basically, they are released from multivesicular bodies. Then there are also apoptotic bodies, which are bigger entities, and they are released when a cell dies. Where are they? Well, basically, this question is really easy to answer. They are everywhere. Each body fluid in our body contains them. Breast milk, blood, prostate secretion, plasma, they all contain them, but not only them. Cow milk can contain it, and even beer has a lot of vesicles released by yeast during the fermentation process. So we can actually say that on a Saturday night in London, we fancy a pint of vesicles, not a beer. So they are known since a long time. In 1967, they were already called platelet dust, but they became more interesting in science during the last 2 decades of this century, when people discovered that they can contain RNA, lipid, and proteins. Most importantly, they have markers on their surface that can tell from what cells they were released. But not only this. Basically, the environment that was exposed to the cells that released them tells other features and other characteristics of these vesicles. And this is called microvesicles heterogeneity. When I was studying these vesicles, I read a lot of papers, and I found this nice paper speaking about a certain type of cancer cells, no matter what they are. And when there was a lack of oxygens, these cells were able to release vesicles, different vesicles, which had a strong angiogenic and vascular effect to the endothelium. Basically, these vesicles were telling to our body to build new vessels to allow these cells, cancer cells, to grow and to survive. This example is not only really important because it tells that these vesicles can be different. This is also really good to understand that cells can communicate through these tiny little things. Vesicles are used by the cells to communicate. They are the language of the cells. But what if we could listen to them? Maybe we could understand their physiological and pathological functions better. Maybe we can use them. But as always happens in science, nothing is so simple. So, as I said to you before, every single cell in our body can release vesicles. And each cell in one time can release millions of them, so we are plenty with them. How can we listen to this chatter? It's like over-listening a conversation when there are a lot of people in the same room, and you can never find the right speech and what you want really to listen. Again, how can we do this? Well, when I was preparing this presentation, and I have to say, I had no idea what a TED was before this workshop, not really. I went on the website and I tried to look at different presentations, and after a few of them, I found this nice talk given by Professor Joan Skog from Harvard University, speaking about exosomes, which, as I told you before, they are part of the big family where the microvesicles are. Basically, it was saying that the markers on the surface of these vesicles are actually like a FedEx shipment label that it tells from what cells they were released. And nowadays, we are able to fish or to catch them with different techniques. Which one? Well, I'm using the image stream and the nano tracker. They are cool machine, even if I'm having trouble with them, but probably it's me not understanding them, it's not their fault. And what can they do? They can count the vesicles, they can visualize them, but most importantly, if you label the vesicles with different fluorescence color, you can actually look at different features of them. These are on the right, these are some of my results, really early results, they don't say a lot. But in any case, you can see that actually you can label the different vesicles with different colors and they tell you different things. So basically, what will be the aim of my project? Well, I will try to simulate the vascular inflammation with different stimuli, and I will apply them to the cells of the innate immune system, mostly to the monocytes, and I will see what kind of vesicles they can release, but not only this. Monocytes can be happy in a physiological way, or sad when they have a pathological status. I can try to apply this stimuli to them in the different way and see if these vesicles are like a mirror of their status, if this vesicle can change. And finally, I will try to apply these vesicles to to other cells, for example, the endothelial or the endothelial cells or the platelets, and see how do they behave and if actually these vesicles can be mirrors of the cells that release them. Why the monocytes? Well, it's really easy. They're not studied. Vesicles from the monocytes are a new field, and nobody seems to have a lot of interest on them, so I can work on them easily. I really would like now to thank you all for your attention, but before, I should say that this is only the point, my study is only the point of an iceberg. There are still lots of things that we don't know about them. Lots, like, for example, how do they are released? Why do they are released? Why they are so heterogeneous? Well, we don't know. I'm sure, I think, I cannot be sure in science, I think that if we find the answer to these questions and we put all the things that we already know about them, we will then be really able to understand them and to use them maybe as a new diagnostic or a new therapy. Last but not the least, I really need to thank you, my lab, especially Mauro and Heffin Jones, which are helping me with my project. And I have to say they are really patient with me. And Annabelle, which is helping me to have a great time in London. And also Jean-Paul that helped us all with this presentation. Thank you very much.